Okay, so welcome everybody to another session of the seminar of the International Institute of Physics. So our speaker today is Javier Magan from the Balseiro Institute in Bariloche Atomic Center. He asked me not to make a very long introduction, but I cannot resist but mention that he was one of the first postdocs here at the Institute, so it is a great pleasure for me to meet him and to see him here again. He always was interested in black holes, so today he will talk about his uh, current understanding of problem of black hole microstates. So, Javier, please.
Okay, hi everybody. I want to start by thanking Dimitri for the invitation to spend here 1 month. So as he said, I was a postdoc around 10 years ago. So it's a great pleasure to be back and to see the new building. And to be back in Natal. So today I'm going to present some work I did in collaboration with Vijay Balasubramanian, Albion Lawrence, and Martin Sasieta. And I will also include further results of a companion work in collaboration with Ana Clement, Roberto Emparan, Martín Sasieta, and Alejandro Vilar. All these works deal with a proposal for explaining the statistical origin of black hole entropy. And although this is quite a known problem, a known topic, let me start with by giving some context. So it is plain that all the existing derivations of the iconic black hole entropy formula, this Bekenstein-Hawking area over 4G formula, all of them have something unsatisfactory to them. So, for example, the main tool to derive this formula is the Gibbons-Hawking gravitational partition function, or the also known as the Euclidean approach to quantum gravity. There are many advantages of this approach, and maybe the main one is that it is universally valid. So it applies, it allows us to compute the black hole entropy formula for basically all known black holes. But also another advantage is that it allows us to compute quantum corrections. And indeed, this is very important because in certain scenarios, quantum corrections can be even, they might stop being subleading. But of course, it has its disadvantages. This approach does not count the states. We lose control about the putative nature of black hole microstates, and we lose also control about the statistical origin of this entropy. Maybe another way of looking at this is that entropy in this approach arises from a saddle point, not from a one-loop trace, and this makes very mysterious the understanding of this entropy as a counting of certain microstates. A conceptually different approach could be called an also very well-known approach could be called the Strominger-Baffa type of countings in string theory. So the advantage of these approaches is that they actually count the states. Actually, they provide orthonormal basis of microstates, which is something very powerful. But these approaches actually have also many disadvantages. The two main ones are, the first is that these approaches are not universal, are very restrictive. So they only apply to a very restricted set of black holes, namely those black holes with high amount of supersymmetry in very particular dimensions and for very particular theories, like superstring theory. The second one is that these approaches do not really count black hole microstates. They count the states of weakly gravitating systems in the limit in which the string coupling goes to 0, and therefore we again lose control about the nature of black hole microstates. So of course this raises several questions. Let me mention 3 that will settle the theme of the talk. So the first question is, what is a microstate? What do we mean with a microstate? This might seem a naive question, and maybe every of you have an answer to this question. But if you look to the literature, different communities have different answers to this question, so it would be good to, and there have been a lot of confusion around the topic. So we will start by reviewing the proper definition of microstate, and it will apply nicely to the problem of black holes. The second question, which sets the core of the talk, is whether we can construct universal sets of black hole microstates, and ideally whether we can count them and prove that that they span a Hilbert space of the right dimensionality, namely of the Bekenstein with the Bekenstein-Hawking dimensionality. And finally, we want to ask whether this construction can accommodate quantum corrections. So in a way, what we want is like an approach that oversees the previous approaches, in the sense that it has all the advantages of each of those, and potentially no disadvantage. We will comment this at the end of the talk again. Okay, so let me start with the first question. So what is a microstate? So the right place to look for the definition of a microstate is in quantum statistical mechanics. Okay, so first of all, it is important to remark that a microstate is, to start with, just a pure state. Okay, so and there should be an intrinsic definition of a microstate that doesn't depend on the basis that I choose to expand the Hilbert space, namely whether I choose to expand the Hilbert space in the energy basis of a certain Hamiltonian, or whether I choose to expand the Hilbert space in a stringy basis in a string theory. This shouldn't depend on that. There should be some physical intrinsic definition. And the definition is this one here. Well, there are variations, but all of them will be the same, basically, for the application to black holes. Is that, let me say, this is a strong notion of a microstate. So it is a pure state that is indistinguishable from the thermal ensemble. What does this mean? This means exactly these equations here. So it means that if I compute in the microstate the expectation value of conserved charges, such as the Hamiltonian, could be the Hamiltonian, electric charge, momentum, whatever conserved charges, or relaxation phenomena like 1-point functions, 2-point functions, time-dependent relaxation phenomena, these expectation values should be very well approximated by the same expectation values, but now in the thermal ensemble. This is kind of strong in the sense that you see this is a pure state. It has entropy 0, and this is now a thermal state which has, from the canonical point of view, it has maximal entropy. And still, the two are the same. So basically, this kind of proving these kind of relations amount to prove that the system in question can, we say, thermalize in an isolated manner at the quantum level. Okay. So let me say that sometimes the problem of finding black hole microstates is associated to, let's say, to quantum gravity and black holes, but there is a starting problem that actually applies much more broadly. And basically, one think it twice and go to the literature. There is no example of these microstates anywhere. Of course, we don't care so much, because in a spin system that is chaotic, we just say, well, there is not really a conceptual problem. There is going to be a Hilbert space, so these states are going to be there. I don't care whether I can construct them explicitly. But if we need to construct them explicitly, you can convince themselves that it is very difficult. And actually, there are basically no examples. And what is the reason? You see, for example, just imagine first computing these quantities in a strongly interacting chaotic theory. There are not really examples of this. For example, of computing the chaos exponent. They just recently in SYK. So this is the partition function in the strongly this would be like computing the partition function in a strongly coupled chaotic system. So these relations are very difficult to compute, let alone construct one of these pure states and computing the same quantities and proving that they are well approximated in the thermodynamic limit by this other quantity. It's a very difficult problem. Okay, it seems almost hopeless. Of course, you could say, well, we know examples. If you take a system with 10 spins or 15 spins, you can just plug into your computer and the Hamiltonian is a matrix. You can diagonalize it and find the eigenvectors, and this would and construct examples of this state. But of course, we want something. We are talking here about something in the thermodynamic limit. We want microstates of a system in the thermodynamic limit, and this seems not to be at our disposal. So what do we do? What are examples of this? So the first obvious candidates for microstates are the energy eigenstates of the system, and this is called the eigenstate thermalization hypothesis, proposed a long time ago, but that has played a very big role in the past decade. So this hypothesis is well, first notice is a hypothesis. So basically, many people just dedicated research to try to say, well, let's try to prove that this Hamiltonian that is chaotic actually satisfies the hypothesis. But this hypothesis, let's say in the softer version, it exactly says that the energy eigenstates of a chaotic Hamiltonian satisfy this relation. Basically, it says that the energy eigenstates of a chaotic Hamiltonian are indistinguishable from the thermal density matrix. But again, we don't have examples of energy eigenstates in the thermodynamic limit. Again, we can compute a spin system with 10 spins, maybe. But if I give you a chaotic spin chain with 1,000 of spins, nobody knows how to write this guy. Nobody knows how to write one of these guys. Okay, so this is not very useful for our purposes. Of course, it would be much more powerful if we could, that's for sure. But still, it's not very useful. So luckily for us, there have been in recent years there have been other type of ideas, other type of examples. The first examples, to my knowledge, occur in the so-called Saz-Debye-Kitaev model, which is a model of interacting fermions, interacting Majorana fermions. And in this model, which is a 0+1 dimensional model, Corculo and Maldacena propose this kind of states. Okay, so they started with some, let me call a simple state. So just this B state is just a state in the computational basis of the fermion. So it's just some 0, 1, 1, 0, 0, 0, 1, 1, something like that. So it's a very simple state that doesn't satisfy these equations, of course. It's not a microstate. But then they evolve it with the Hamiltonian in the Euclidean direction for a certain amount of time. And they get some state. The physics here is that you started with some state with average energy that is high, and then you, with this evolution, you project it down to lower energies, and then you find some state at lower energies that now is a little bit more random, and actually one can prove that it satisfies analog of these equations. Yes. Yeah, this arrow means in the thermodynamic limit. So this should be, if you want, this you could substitute the arrow with equals and put here order 1 over the entropy or e to the minus the entropy. I don't want to enter. I mean, this, of course, yeah. You could try to discuss better, like what kind of degrees of chaos you could have by the scaling of that error. But that won't really matter for black holes. So actually, we can avoid that technicality. But yeah, here I'm just assuming that there is. So this is an equal, and then this is. Of course, it cannot be equal, okay, because the two things are different. But I mean, this. Yeah, this, for example, is. Yeah, there might be time independence here, and there might be time independence here. So it is really different thing. But the point is that the error is decaying in the thermodynamic limit. Okay. Time dependence disappear. Yes, can disappear. Well, because you can be on average you can be constant, but in the real thing you can be like this. Okay. Okay. So further examples that appear in this article by Goelam, Turiachi, and Berlinde shortly after. This was inspired by the in JT gravity. JT gravity is a theory, is probably the simplest theory of gravity in 2 dimensions, and well, it's the simplest theory of gravity. It's a theory in 2 dimensions, and well, it has been studied very much in recent years. And here one can construct this what they call partially entangled thermal states, which basically arise by inserting an operator in the thermal cycle. We are going to see it in a moment. And this form basically the main motivation from for our construction. In this case, again, one can prove, in this case, actually, they can really prove that these states for JT gravity, they satisfy these relations. Okay. Okay. So, well, this motivates a little bit the question that we want to ask. The first question. So, we want to, ideally we would want a generic conformal field theory method to construct microstates in the sense of quantum statistical mechanics. So, I'm going to present a proposal. So, so we can construct an insightful set of quantum states in conformal field theories by considering so-called dust-cell operators. So a dust-cell operator is defined here. So it is a complex operator that is formed by inserting many operators around the spatial slice where the CFT lives. Okay. So for example, let's say that it lives in a sphere. So the spatial slice is labeled by angles, the positions. So I'm going to insert a seed operator. So I take one seed operator, one primary in the CFT. I take one. I consider the seed, and then I just insert many operators along the sphere. So this dust cell operator is labeled by the insertion angles and the number of insertions. Okay. In what follows, we are going to assume that we put the insertion angles homogeneously distributed over the sphere. So we will not worry about the angles, and the only label for us will be the number of insertions. Okay. So here we call it a dust cell operator because this is exactly well, it's an operator that creates a gas. No, I create a particle here, so on and so forth. So it creates a gas of particles that, in principle, if the particles are sufficiently separated, it's even free. So it's a very simple. I mean, it's a complex operator from a certain point of view. It's also kind of a physical simple operator from another point of view. Okay. So using this operator, these operators, we can use now the usual path integral methods to construct states in the double Hilbert space of the CFT. So I don't know if people is familiar with the path integral method, so I'm going to define it. So typically, when we talk about path integral methods, what people refer is that well, they use the Euclidean continuation of the single theory. So imagine divided this in two. So then I evolve with certain Euclidean amount of time. I insert an operator. Here it would be the O dust. I evolve again certain amount of Euclidean time, and then here at this slice, I analytically continue. Okay, here I'm not analytically continue. I'm putting the full Euclidean solution, but let's consider analytical continuation here at the time symmetric slice. And this procedure naturally defines a state in the double Hilbert space. Okay. For example, the Hartree-Hawking state for the black hole, it just putting here O dust to be the identity instead of O dust, and then this is just Euclidean evolution, and this creates the thermophile double, which is the eternal black hole or the Hartree-Hawking state for the black hole in a theory that describes black holes. But we can insert other operators, and this will create different states. Well, this is the intuition. If you didn't like the intuition, let me just define it properly. So there is a natural, let's say, if you want isomorphism between operators in the original theory. In this case, a CFT. We have a CFT, some operator, and then we duplicate the theory. So now in the double Hilbert space, which is just the tensor product of the Hilbert space of the same Hilbert space, the original Hilbert space, wave functions can be characterized by a function of two labeled by two energies, and then from this operator I just define these entries to be the amplitude to go from eigenstate E to B to eigenstate A, follow by this string of operators. No, so I evolve Euclidean time for a certain amount. Here should be O dust. Sorry, I introduce O dust, and then I evolve for further time. Okay, this is a standard construction of operators. I mean, of states starting from operators. It is also used in the quantum information literature. Okay. What?
Did you mention that you understand this in the paradigm of ADS safety, so define like safety operators in principle? You're talking about something.
Well, I want to, yeah, I want to make the point that this is a CFT proposal. I'm making a CFT proposal here, and now, for the moment, not necessarily. This is a CFT proposal, and you could study for the easing model. Okay, you could consider the easing field and put in, yeah, and run and you can construct these states here, and you can study them. Okay, yeah. So this is a generic proposal, and actually, for constructing microstates, let me explain the intuition a little bit. The intuition is that so to satisfy these equations, what we really want is to create. So we expect that these equations are going to be satisfied when this pure state is sufficiently random, for some reason. Okay. Of course, we can create random states in many ways. The only thing is that it's difficult to create a random state and still keep control about it. So we need some method to construct sufficiently random states and still keep control on the state. Okay, that's the game. So this is a proposal for. I mean, there might be many other proposals. This is a proposal for playing that game. And why is this proposal expected to construct something like a random state? Well, it's expected to construct something like a random state, or at least something more random than when I started, because if I'm in a strongly chaotic theory, this operator, when I multiply many, in the operator product expansion, it will be supported in the energy basis in a very random way, because there is no reason to expect anything particular, any structure. Okay. But there is a problem. You could say, well, but this way, if you introduce, I don't know, any insertion, or you introduce n prime insertions, the states that you will construct are very different in energies, and you want to construct microstates, all of them for the same energy. Okay, so you are making a mistake. This state will have average energy n times the energy of this operator, so the scaling dimension of this operator, so n times delta. You put another number of insertions, it will have another energy. So, and in principle, if you put infinite insertions, it will have infinite energy. So it won't contribute to the band, to the energy band you want it to contribute. So the solution to this is that we don't only consider this, we consider this plus. So the operator we really consider is the O dust plus the Euclidean evolution that projects a little bit down to energy. And actually, this Euclidean evolution, I put here beta tilde, that you might have wondered why beta tilde and not beta. I put beta tilde exactly because it's not the physical temperature, in principle. I will achieve a microstate for a physical temperature beta, but to do that, I will evolve with certain a free parameter beta tilde that is free for me to use at my disposal. Okay, and we are going to see how I use it. In principle, it's just free. Okay. You mean the dimension here of this guy? A circle? So here the CFT lives in a circle or in a sphere. What? Yes. It can be in a circle. Yeah. It can be a one. Sorry. It can be a 1+1 dimensional CFT. Yeah. We expect. Yeah. We have the construction also for the 1+1 dimensional CFT. Yeah. I thought you were referring to the dimension of the scaling dimension, so I confused. So are there more questions? Okay. So but this is still okay. This is just a proposal. It seems taken out of the hat. There's no reason. Basically, there's these intuitive reasons that I kind of constructing some complex operator and then projecting down to lower energies. But still, of course, the main question remains: how do we show the strong notion or the weak notion? So here, I want to remark that we believe this proposal to be valid for generic CFTs. I mean, for strongly interacting CFTs. But we were not, and this is an interesting question for future research. But so we were not able to prove it, but we were able to prove it for holographic theories. Okay, so how do we prove it for holographic theories? The trick is to tune the states, which here means we have three parameters. We have the number of insertions and these preparation temperatures. I will call this this beta tilde the preparation temperatures, because they kind of prepare the state, okay? The amount of Euclidean evolution that I use. So I have two free parameters, the number of insertions and beta tilde. So my claim is that, so the trick is to tune the states, to tune these parameters to lock the information of the perturbation behind the horizon of a black hole, okay? Yeah, so yeah, one thing is a strong coupling. Here a strong coupling, I just want it so that the theory is chaotic, and then I expect to find microstates of this sort, because if not, I don't understand very much how the system thermalizes in isolated manner. Of course, I can put it in the thermal ensemble, a free theory, but I don't expect to have microstates of this sort. So one thing is that I want it to be strongly interacting or strongly chaotic, just for this to be the case. Now I add another condition, which is that this theory is holographic, okay? Which basically there are further conditions here applying, okay? So if the theory is holographic, I can try to do this, so to lock the information of the perturbation behind the horizon, and so let me. And the claim is that this is possible. The claim is that this is possible, and this is possible because basically these CFT microstates have effective descriptions in the bulk. So using the standard holographic correspondence, the standard holographic dictionary, these operators, these dust cell operators, are dual to a domain wall with a perfect fluid localized on its Ward volume. Okay, so in the bulk, these states are described just by let's say, by a bubble with a gas localized on it. Okay. Now, because we put the insertions homogeneously distributed over the cell, over the spatial slice of the CFT, here we have a spherical symmetry, and then Birkhoff theorem tells us that the geometries outside, I mean, at one side or at the other side, are both black hole geometries. Okay. So the only thing that I need to do to solve the equations of general relativity is to ensure that so-called Israel junction conditions are satisfied. So for people that are not familiar, Israel junction conditions are conditions that are basically the very same equations of general relativity, but when applied to a thin cell that affects a transition between two different geometries. Okay, it's exactly what we need here. We need the conditions that ensure that these two geometries, one black hole here and one black hole there, with the same mass or different masses, one can transition from one to the other when there is a cell with a certain stress tensor. Okay, the Israel junction condition typically reduces the problem to a one-dimensional problem, namely the trajectory of this cell over the bulk. And what I don't want to enter in the details, so here everything can be computed analytically. But let me here for the sake of the talk, I just want to say that these equations are very permissive. There are no so one would like to see what are the constraints to find the solution, and there are basically no constraints. The only constraint is the only consistency relation is a relation between the physical temperature of the black hole that we have created. So here in the right and here in the left, the black hole that we have created, and the preparation temperature, the beta tilde, at the time of flight of the cell. Basically, the time it took the cell to go from here, twice the time. This delta tau is twice the time it took the cell to go from here to the time symmetric slice. So this equation, I cannot explain it here. It follows from the equations of motion. I just want to remark that there is a very simple heuristic derivation of it, which is just if we look at the if we look here at the solution, and this time here, the time it takes the dust cell to go from one side to the other is delta tau, and this is beta tilde. And we know also that if there would be a black hole here, the periodicity in the time direction would be exactly the physical temperature. So it has to be the case that the physical temperature, which is this periodicity, is equal to the sum of the preparation temperature plus the time of flight of the dust cell. Well, these are a bit technicalities, but the important point is that this relation is very permissive. In what sense? In the sense that I can fix like to start with, I can fix the physical temperature because I want to create microstates for a physical temperature. So I fix it for the start, and then I can put any number of insertions that I want. Here, delta tau basically depends on the number of insertions because the number of insertions tell us the mass of the cell, which dualize to the energy density in the cell in the bulk, and this controls the time of flight. Okay, so this time of flight depends on the physical temperature as well and the number of insertions. But then I can fix the physical temperature. I can fix the number of insertions, the mass of the cell, as I want, and still I can solve this equation by just choosing beta tilde accordingly. Okay. So the conclusion, this is one of the most important conclusions, if you want to take home, is that this way we can construct infinite families of black hole microstates labeled by the mass of the cell. Okay, so for any mass of the cell, like fixing some temperature, for any mass of the cell, I can find one of these solutions. Okay, and if it was not clear, let me answer why this is a microstate. So this is a microstate exactly in the sense of quantum statistical mechanics that we discussed before. Why? Because the geometry outside is the same as the usual black hole geometry. And therefore, I don't know how many people is familiar with computation using black holes, but any type of conserved charge or any type of relaxation function only depends on the stereo geometry. They don't depend on the interior aspects of black holes. Okay, so these quantities, if you compute these quantities here, so these quantities, sorry, in this microstate, they will be exactly the ones as if I wouldn't have put the insertion. So it would be exactly the thermal case. So the black hole case. Okay. Let me also say that an effect of this, an important effect of this cell. So typically, if I don't put the cell, the diagram that you have typically seen is the one of the eternal black hole, which is this. With only one horizon here. I mean, one bifurcated horizon. And here, what happens is that basically the cell. So so this would be the Einstein-Rosen bridge. Here, what happens is that the cell has stretched the Einstein-Rosen bridge, and one can compute the volume of that stretching and relate it to the mass of the cell. So find a very simple relation. And actually, this has a kind of very nice interpretations in terms of holographic complexity proposals and so on and so forth. But we won't talk about that today. Other questions? Well, these are just different views of the geometry. So again, this is here. This is the spatial slice. So at time equal to 0, typically there would be no two horizons, not two black circles. There would be only one. So the geometry would be something like this. Okay, it will the spheres, the area of spheres will be decreasing until the horizon, where in the horizon would be minimal. While here there is a stretching, and then the spheres grow again inside the horizon. Well, not so very important. Okay, so let me say that this construction is very universal. So we have one can do it for charged Rice and Nostrum black holes in ADS with ADS asymptotics or flat asymptotics. One can do it for rotating Myers-Berry black holes. One can do it for a near extremal BPS and non-BPS, and there are two different constructions in this case. One can do it for the BTC black hole in 3 dimensions, dual to a 1+1 dimensional CFT. And there will be some critiques that these were very effective description of black hole microstates, but it's important and that the microstates will not be like that in top-down theories. And actually, this is not true. One can construct these microstates in string theory as well. So in n equal to 4 superjam mills. And the construction goes by, I mean, there are many different possibilities, but one possibility is to consider type 2b supergravity solutions of this sort. This type of compactifications, so it's a compactification on a sphere S5, done to ADS5 with certain metric, and this type of compactifications play a big role at the early times of ADS-CFT. But here we can use them to construct microstates in the same manner, since at low energies, basically, we have Einstein-Maxwell theory again. Okay. The only subtlety is that if one wishes to construct the cell with a seed operator that is that has low dimension, then one runs into a small problem, because every field at low energies in n equal to 4 super Mills is charged, have particular charges. Okay, so then in principle one arrives to cells that are charged, but that is not a problem. One just need to put so one need to because actually this thing can be generalized. Sorry, to put in more than one cell. Okay, so this will be the time symmetric slice. Here we have a cell with certain charge plus, certain charge minus, and here are the horizons. So we can do the same, just that we need to put, instead of one cell, we need to put 2 cells, okay, or more cells. Okay. So let me stop here a little bit and make a small summary and some remarks, okay. So first, notice that the construction is kind of very economic. We only needed a not so heavy operator, this seed operator in the CFT. Okay, so this type of microstates are there for general relativity or Einstein-Maxwell, just adding a scalar field with certain mass. Okay, but therefore they are also there in string theory, for example, in n equal to 4 super Mills, and in any quantum gravity of theory that has, as its low energy approximation, general relativity plus a massive particle. Okay. So that's a comment. Another one is that notice that all these microstates, which are perfectly defined states in the boundary, they are very precise states. They have semi-classical descriptions that are geometric. Okay, this is counterintuitive, and this lies at the origin of why the gravitational path integral is so powerful. And notice that these geometric approximations of the state or description of the state have singularities and horizons. This is important because it kind of shows that some of the assumptions in the fastball program were at the very least misguided. So people in the past have been looking for microstates that are horizonless and with no singularities. And here we are finding microstates that have singularities and horizons, and we see that it is not really a problem of the state. The state is perfectly well defined in the CFT. Okay, we will have the CFT, full control of the CFT. This wouldn't have any type of problem of this sort. It's just the leading semi-classical description that has that problem. Okay, but what this is telling is that most microstates have this structure, and we expect now that it is it might be not a bug, but a feature that microstate show this structure. Again, it is important to notice that the Einstein-Rosen bridge grows indefinitely with the scaling dimension of the operator, and this connects very well with the holographic complexity proposals. Basically, these states are expected to be very random. Now, moving forward, these infinite families of states that are geometric naively overcount black hole entropy. Okay, one would expect that if I have very different states with very different semi-classical approximation, they can expand. I mean, they are almost orthogonal to each other, and they will expand a Hilbert space here of infinite dimension because we have infinite amount of states. This is a sharpened version of a problem that was not was known in the literature. It comes under the name of Wheeler-Bacoff-Gold geometries, and it was studied before, but it was not maybe taken with some seriousness, because basically it was thought that let's dismiss these geometries. we don't expect these geometries to contribute to the black hole Hilbert space that is formed by collapse. Okay, and this is kind of natural because these geometries are just, I don't know, it's a geometry with something inside, but how do you know that this geometry contributes to the same Hilbert space of black holes formed by collapse? Okay, but so it was a question that was more or less dismissed. But here we have arrived to these geometries just by an ADS-CFT construction. So these states are really states in the CFT. And in the CFT, they are bounded by the entropy of the CFT, which is the entropy of the black hole. So it is very difficult to argue that these states do not contribute to the black hole Hilbert space, and we need to do something. We need to face the problem. We need to do something about it. And the question is whether they really overcount the entropy or not. And to answer this question, we have to learn how to count them. Okay. So I'm going to come to this question in a few minutes. Let me just say that in principle, any Hilbert space has an infinite number of states. Even a 1 qubit has an infinite number of states. Of course, the question is not how many states there are in a Hilbert space; it's how many orthogonal states are. No, that is what sets the dimension of the Hilbert space. So what we learn, what we need to do is not to get confused about how many states we can construct, but we need to learn how to compute how many of them are linearly independent. Okay, and linear algebra tell us that to answer that question, we really need to compute the inner products. Okay, the inner product between the different states. So here we are going to compute the inner products and the products of inner products. Here the overline notation means that we are going to compute these quantities using the gravitational action. I don't know if people is familiar with this way of computing in quantum gravity, but it's just a generalization of the Gibbons-Hawking partition function approach. Basically, one sets some boundary conditions, pertaining to the microstates in question, and then fill in the geometry that solves the Einstein equations, okay? That solves the equations that follow from this action. This is, for example, I mean, this is I say this is a generalization. Okay, let me come back. One moment. So, this is the geometry, the type of geometries that we have, the Euclidean geometries that correspond to these microstates. This is a generalization to the Gibbons-Hawking approach in the sense that the Gibbons-Hawking approach would be just to put here the identity operator, and then we would just have Euclidean evolution. I mean, Euclidean Hamiltonian evolution, which would create the thermofield double here. And but the ideology would be the same. That would be the thermofield double. If I want to compute the norm of the thermofield double, I just put the bra and the ket that gives me the full boundary conditions, which is symmetric in the thermal cycle. And then I fill in the geometry with the Euclidean black hole. I compute the action of the black hole, and that gives me the partition function of the theory. Okay, we are going to do just the same thing, the very same thing, but for these modified boundary conditions. So here would be the norm. This would be the norm. This would be the square. We are going to see it in a moment. In any case, the structure, so this would be, so its inner product corresponds to one boundary, okay? So this corresponds to a one boundary problem, this corresponds to a two boundary problem, this corresponds to a three boundary problem, and we can order all this computation by the connected contribution. So the n boundary problem will have this structure as the ratio between an n boundary solution, an n boundary wormhole, and normalized by all the norms of each individual state that that I didn't put them when I construct this. When I construct here a state with this is so in this path integral construction. Typically, when I construct states with the path integral construction, these states are not normalized. So I need to compute the norm, which is just this quantity that I put here, and divide by the norm. Okay, so these are just normalizations. Those are technicalities. If somebody's interested about the technicalities later, we can discuss them. Let's just go a little bit about around these solutions. So the first solution is exactly the one that computes the norm of the microstate. Okay, so it is exactly like the Gibbons-Hawking Euclidean black hole, just that now the geometry is cut by the cell, where we need to enforce Israel junction conditions. Okay, but otherwise it's very much the same, and the action can be computed. More interesting is the square. Okay, so the square has two boundaries. So this is one boundary where we put some inner product, and this is another boundary where we put another inner product. Now, these boundary conditions have two contributions. One would be, so I have two boundary conditions, one circle here, one boundary, and one boundary here. I of course have one contribution which is the same as the norm. So I fill in the geometry like by the previous one. Okay, this would be the disconnected contribution. But the interesting thing is that with the cell here. But the interesting thing is that there is another solution in which now, which is connected geometrically, in which now the cells travel from one boundary to the other. So in this way. Okay, so we have a cylindrical wormhole. Okay, maybe this is a little bit for the people that have not worked on this a little bit challenging to understand, but actually I want to claim it's not so difficult to understand if one just open the wormhole. And then what we have is just two Euclidean black holes. This is one, and this is another. And they are cut into so I have two Euclidean black holes, one here and one here. And I cut the two with two cells. So here I cut this one with cell 1, and I cut this one with cell 2 in the other side. Here I can do it in the same way as the previous solution. This of course is not a stable solution, but I do the same with the second one. And now I glue them each one with each one. Okay, this with this and this with this. So I get a cylindrical wormhole. It's a very well. I can talk more about that later. These wormholes were discovered by Chandra and Harman and independently by Sasieta, and they can be seen as a generalization of the wormholes found by Stanford in JT gravity. And they can be generalized to more boundaries very easily by the same cutting and gluing procedure. You just cut more times the Euclidean black hole and glue it with the other. Okay, let me say that all these actions, I mean, and now we need to compute, so these are the solutions. One need to compute the action of these solutions. Let me say that the action can be computed. It's not so simple, but it's not so complicated either. It can be computed analytically even. Of course, it gets a little bit tedious when one includes more boundaries, but it can be done. But it is very important for the next steps that a very strong simplification occurs in the limit in which the cell has a very large mass. In this limit, basically one can show that the time elapsed by the cell, this delta tau that we had before, goes to 0. Okay, so basically the cells like pinch the geometries. Okay, so and leaving just two black holes here, full black holes. And then the action of this solution in the limit of the largest mass is basically the Gibbons-Hawking partition function for a modified temperature. Okay, so let me explain it another way. This kind of, you can understand this as a reinterpretation of the Gibbons-Hawking partition function. So typically the Gibbons-Hawking partition function, this C over beta is interpreted. Let's say let's put here some question mark, but it's interpreted at the trace of e to the minus beta h, certain Hamiltonian. It's just the partition function of a given Hamiltonian described in the black hole. Here, it arises with a different application, with a different meaning. What it's telling us is informing us about the noise, about the size of the inner products between different black hole microstates. Okay, it's very different interpretation. Okay. Now, for the people in the audience that is familiar with a little bit with the field of quantum chaos and random matrix theory, they would recognize here this quantity as what is called the plateau of the spectral form factor. Okay, and it's a very difficult quantity to compute typically in the way people compute it. And here we just get it on the nose, basically, with this other using these cells. Okay, I will comment about this a little bit more later. Well, it's not special. It's a very typical case, you see, because we have microstates for any mass. So most microstates have large masses. Is the most typical. This is exactly the most. This is a limit that is very physical. It's the limit of. It's not a special limit. It's actually the typical limit, you could say. Yeah, good question. So the same happens. The same happens with for the M-boundary wormhole. And one just get the Gibbons-Hawking partition function for m beta instead of 2 beta. Again, it's like a generalization of the plateau. Okay, so these are technically the main results of our articles, and they follow for all classes of black holes. They say they basically one can understand them as setting the statistics of inner products between infinite families of black hole microstates in terms of the Gibbons-Hawking partition function. Okay. Are there questions about this? Maybe this is a little bit unfamiliar to many people, but yeah, if one wants to get something home, these formulas are very important. Okay, so let's go to the last part of the talk. So with this information, now we want to ask, what is the Hilbert space dimension? So as I said before, the Hilbert space dimension is not the number of states that we have at our disposal, it's the number of orthogonal states. Okay, and for a set, generically, for a set of states, psi p, let's say with p going from 1 to omega, the Hilbert space dimension is just the rank of the Gram matrix of overlaps. So I just have this is a matrix omega times omega. If I have omega states, this is a matrix omega times omega of overlaps. And then I compute the rank of that matrix, and that is the number of linearly independent states. So the goal is to compute the rank of the Gram matrix using the results from the gravity computation. Namely that because the gravity computation, notice that exactly has computed something about this matrix, basically the powers of that matrix. The question is, if with that information, can we extract the rank or not? And the answer is yes. So the rank is the number of non-zero eigenvalues, and the number of non-zero eigenvalues follows from the density of states. Okay, so what we need to compute is the density of states, and the density of states can be computed with techniques of random matrix theory, basically computing the resolvant of the matrix first, and then computing the density of states. I will not review that. This is completely parallel to the discussion of replicant wormholes in the paper by Pennington, Schenker, Stanford, and Young. And the end result is this formula here for the density of states in terms of the number of omega microstates that we have just taken, and where S here, bold phase S, is twice the Bekenstein-Hawking entropy. We are going to get in a moment twice the Bekenstein-Hawking entropy, but this is just expected because we are constructing microstates for the double Hilbert space. Okay, so we are constructing microstates for the double Hilbert space. This is, I just use this one because it's more transparent, technically easier, but in the article you can find also the generalization to single-sided black holes, but it's not very important. But here we get twice. Here we get twice. So this formula. So using this formula, this density of states that follows from the gravitational results, we can compute the rank of the Gram matrix as a function of the number of states that we take. So we can take, as I mentioned here, the natural thing to take is to take some microstate with cell mass m, sufficiently large, and then take like a set of omega microstates with masses mp equal to pm with p1 until omega. Okay? So this I can move omega and take larger and larger sets of microstates. And the rank it grows linearly with omega at the beginning. Okay, so this means that I take one microstate, it generates a Hilbert space of dimension 1. I take 2 microstates, it generates a Hilbert space with dimension 2, and so on and so forth. So basically, this says that every time I add a new microstate, it points in a new direction in the Hilbert space, until I reach the Bekenstein-Hawking degeneracy. In that moment, adding more microstates doesn't increase the rank, which means that the following microstates are linearly dependent superpositions of the previous one. This is very striking, not only, I mean, as an explanation of black hole entropy, but notice that these are very geometric states. So this is saying that this very different, I mean, geometric and very different. So even the interior, the volume in the interior for the new state that I'm putting is very different from all the others. So this means that I can expand a black hole with a very large interior with microstates with Einstein-Rosen bridge of a smaller volume. Okay, it's a very dramatic effect. We can discuss that later more, but okay, sorry. Okay, so this is exactly this ends the statistical explanation of black hole entropy. No matter that exactly at the Bekenstein-Hawking degeneracy, no matter how many states I add, the dimension doesn't change. Okay, let me conclude just with a couple of comments. The first is about quantum corrections. So in this sense, maybe this is a little bit for the people very interested, but in the heavy cell limit, the heavy cell limit is also very useful for this because everything boils down to the universal overlaps in terms of the Gibbons-Hawking partition function. But at the same time, in this heavy cell limit, the cell travels through the interior very far from the horizon because I stretch the Einstein-Rosen bridge very much, so the cell travels very far from the horizon in the interior, and the quantum corrections are always kind of related to near horizon physics. Okay, so basically these partition functions contain the information about the quantum corrections, and the universal overlaps does display the quantum corrections, and the entropy that one gets is the quantum corrected one. Okay, when one includes the quantum corrections. And do I have 2 minutes, or I don't know if, yeah. And I want to end with another remark that this kind of construction unifies basically most versions of the information paradox. So, for example, one version is the avatar of the information paradox proposed by Maldacena regarding the long-time behavior of a correlation function. So, in a finite system, correlation functions cannot decay to zero. They have to saturate at an exponentially small value, and but the gravity doesn't see that. Okay, so that's the problem there. But here we can see basically we can have you can see a modification of that problem by seeing the mass of the cell as a time, and then the solution to Maldacena problem in this modified scenario is exactly the solution to the finiteness of the black hole entropy and the right value of the black hole entropy. Going in the opposite direction, we can say that in another modification of Maldacena's version that was explained in this paper regarding the spectral form factor, this spectral form factor can be understood as the physics, by basically is encoded in the physics of the time evolution of the thermofield level, and actually one could take the evolution of the thermofield level as another set of microstates different to this one, and solving the problem of Maldacena would solve the problem of the black hole entropy there. In other direction, this construction generalizes the studies of the page curve into dimensions, to general dimensions, because we just need to take this matrix of overlaps as a toy model of an evaporating density matrix, and one would reproduce the same computations. And finally, there is another problem, which is the saturation of ER bridges. There is this so-called holographic complexity proposals that propose to relate the volume of the Einstein-Rosen bridge with the quantum complexity of the state. These are very bold proposals, and maybe the boldest consequence of those proposals is that complexity can only be exponential in the entropy. Okay, so it says that in a way, from certain perspective, the Einstein-Rosen bridge should plateau. I mean, should have a maximum from certain perspective. And in this case, at least we provided a self-symbol interpretation because, as I said, when I have an Einstein-Rosen bridge that is super exponential, I can always express it as a linear combination of this result implies that this black hole will be expressible as a linear combination of black holes with sub-exponential Einstein-Rosen bridges. So, and there are even toy models that one can use to track the complexity of the Einstein-Rosen bridge. And with this, I finish, and thank you for the attention.
Okay, any questions to Javier? Well, let me probably start with questions. So in the end, in your calculation, where was the randomness of your states? So your construction was somewhat important for random. So your states need to be random.
Well, that's a good question. It's something that we thought. That we tried to solve at some point, and still is, it's an open problem. So it will be good to discuss. Let me just say that maybe the proof of randomness of the states is exactly this. Wait. No, sorry. Here. So this technical result that says the statistics, this could be understood, you can understood as the statistics of these microstates, okay? The fact that they show these statistics, it's very, well, it's a proof of a high degree of randomness. We don't know how to quantify randomness in terms of these statistics properly, and that's the open problem. But this is very this is random matrix theory statistics, basically. It's not random matrix theory. Yeah, that's the problem. It's a good question. We don't really know, but this is a proof that they are very random from certain perspective that we still don't understand.
But the states for which you compute, they're like very specific geometries, which are simple geometries.
Yeah, simple, but still very random. So geometry can codify aspects of randomness. This is a proof of that. Yeah, that's the connection that I was trying to. Yeah.
Or do you take just some representative and you assume that this is like self-averaging, so computing for any representative, which basically mean computing the average or something like that? Again, the geometry that you consider is
the geometry is just the geometry is
the
geometry is just a description of a coarse grain aspect of the state. But the fact that aspects of the geometry tell you that the state is the microscopic state, if you want, the state with the precise numbers. So at the end, the state is some precise state. No, is this state to be precise? Is this state here, no? With these entries. This is a very precise state with very precise entries in the double Hilbert space, okay? And you want to quantify its randomness. That's the question, okay? That's a difficult question. I don't know precisely the answer. I'm saying that a partial answer is the size of the overlaps. I mean, of the size of the inner products between that microstate and itself and other microstates, okay? And yeah, that is codified by the volume of the interior. Okay, yeah, but it's a good question. I don't have more answer than that, but it really connects with the ideas that the black hole interior codifies complexity and randomness.
Another question is about the formula that you use for this path integral formula, which you just flashed it, and we compute the average of main product of many.
This one, no?
Yeah.
Yeah, I'm not computing the average. Here I'm not. I don't need to interpret it as an average.
Right.
I don't want to enter in that interpretation.
So you compute instead something like another thing which looks very much also like a replica trick. And people that study chaotic system or systems with disorder, they compute averages by computing replica.
Yeah, completely.
So-
But in that case, you start with an ensemble of theories. So, for example, SYK or random matrix theory. Okay, and then you have a clear understanding of what everything here means, because those are averages. Here, I'm just saying that I'm going to compute these quantities using the gravitational path integral, and I leave the interpretation for I don't want to enter in that interpretation. I don't need to interpret. That's our point. Of course, the interpretation that we like more is that the gravitational path integral is dual, is really computing some kind of average. Here, it would be an average not over Hamiltonians, but it would be an average of the sort of the Einstein thermalization hypothesis. So it would be an average over the operator entries over these operator entries. So it's really an average. So here, this quantity is going to depend on this energy Einstein state goes through, because these are conserved charges. So this goes through, and this is just basically this psi IB, basically some exponential factors times OAB. Okay, and that OAB is very complex quantity. It's a very complex quantity, and the statistics of that quantity is what the gravitational path integral is capturing. That's the expectation. But I didn't want to enter in that because we don't have any more useful to say in that regard. Yes.
More questions? So I don't know, Rodrigo, maybe you can comment on the this part which is about spin chains and so on. So about construction of states, this is something that Javier started with. That it's impossible to study this even in the case of spin chains, or very hard, or the microstates are not known. I mean, what do you think?
Mm-hmm. So if I understood your point, you don't want integral systems, right? You just
I want a quantum chaotic system. I was just making a point. I was making a point that sometimes many of these problems. So there are many biases, in the approaches in the past decades to this problem, and some of that biases don't recognize that there are problems that have nothing to do with quantum gravity, that go beyond, that are just problems in chaotic theories. Okay. So, for example, if you ask, like, can you construct a black hole microstate? Your mind blows up, and people don't know what to do, and the problem is related to quantum gravity, and it's very difficult because it's something quantum gravity that we don't understand. And actually, that problem it's a more generic problem that we don't know what to do in any chaotic theory. You take a spin chain, and unless it has 10 spins and you can put it in your computer, you won't be able to do it. There are no examples. And actually, black holes, this shows that black holes are the first candidates in which we can construct this type of states.
Right. Yeah. I agree with this statement, essentially, because there are some models where you can, integral models where you can construct exact eigenstates for very large spin chains, but they're not quantum chaotic.
They are not quantum. No, of course, they are integrable.
Models,
they are integrable, of course. They are not quantum chaotic.
And then there are also non-integral models with microstates which evade the eigenstates normalization hypothesis by some other mechanism, but then you're not interested in those cases.
No, I want in the most complex ones. So then the ones that are going to satisfy the equations, and those you need a lot of complexity for those, and then you cannot construct those. Yeah.
Other questions? Okay, if not, let's thank Javier again.
That controls my voice, because I cannot say anything without it being here.